I'm Andrew DeMello, and today I am going to be making an electrochemical battery cell, where the natural wanting of electrons from copper is greater than iron, and that natural drives electrons from an iron electrode to a copper electrode through the voltmeter, which acts as a circuit, and it will read the electric potential differences in this battery. I theoretically calculated this using a table of standard reduction potentials, and the theoretical value is 0.7889 volts. Now that's a standard. This is a standard reduction potential table, meaning it's for the solutions of metals that are in one molarity. But as defined by the Nernst equation, it's going to be the same because both of these, the copper sulfate and iron sulfate solutions, are 0.1 molarity. And so you have the Nernst equation is the standard electric cell potential, which I calculated here and I just showed you, is 0.7889 plus 0.0592 over 2 times the log of Q, which is the concentration of the anode over the concentration of the cathode. And since they're the same and the log of 1 is 0, it's going to be the same as the electric cell, the standard electric cell potential. Okay. We have 3 40 milliliter beakers here. We have a 1 molarity solution of potassium nitrate. This will act as, well, we also have a piece of paper which is acting as the salt bridge. And what this does is I'm going to dip it in the solution of potassium nitrate and fully saturate it to my best ability and connect them and dip it in the cathode and anode, such that when the electrons leave the anode, because copper naturally wants to accept these electrons, there's going to be an imbalance. The iron solution is going to be more positive. So the nitrate, the NO3 negative, is going to go to the left, the anode side, to make it neutral, and the potassium is going to, and since the copper solution side, the copper electrode is going to be accepting electrons, it's going to be becoming more negative, it's going to need to be balanced out, and that's by a positive charge, and that's where the potassium is going to go to balance out that charge. If this charge was not balanced out, the anode side would become so positive that the natural transfer of electrons would stop. So yeah, since the theoretical electric cell potential has been calculated to be in the range of the 2 volt mode, I'm going to be setting the voltmeter to 2 volts, as 200 millivolts would be too low. Okay. So we have our iron electrode, copper electrode, iron's at the cathode, iron's at the anode, yeah, copper's at the cathode. Okay, so we're going to be pouring 40 milliliters of each in their respective beakers. That's a little too much. Doesn't really matter, but I have OCD. Here we go. There's one. That's going to be our anode. pouring 40 milliliters of the copper sulfate solution into the other beaker. And so these are not brand new electrodes, they have been used. So just to ensure, in order to ensure that all the electrons are freed up, I'm going to just scrub them down with steel wool to free up those electrons from the corrosion of past use in order to reduce the error that we get in the end, in order to obtain the closest voltage value to our theoretically calculated. That should be good. And now this is, I already poured the potassium nitrate solution for the salt bridge, and we're going to put our electrodes in their respective cells. Iron, iron, copper, copper. And this is the salt bridge. I'm going to need to fully saturate this to get the most accurate reading. I'm going to be connecting the black lead to the anode and the red lead to the cathode. It's going to be hard to record this, but so right now, just to show, I'm going to connect them before adding this, connecting the two cells with the salt bridge. There's very little, as you can see, there's no voltage reading. Okay. I'm going to disconnect them. Actually, I can leave them here if I'm going to disconnect them. Just so you can see everything, I will prop up this voltmeter so you can see what it reads when I connect these two via salt bridge. So we're going to fully saturate this piece of paper that is acting as our salt bridge, and I'm going to just fill up this beaker a little bit more in order to ensure this. There we go. There we see it's fully submerged, meaning it's going to be fully saturated as the paper absorbs that solution. If I can get this right, connect these before. You can see the voltmeter is not really going to pick up anything. Now, I have everything steadily going. We're going to connect them via salt bridge. And there we go. See, the voltmeter reading is shot up to 57. We got it. There we have it. And that is all. There is a little bit of air, and that could just be because of not having a fully saturated salt bridge, and it's not entirely in the solution. But given that we got a reading of 0.555 volts, it's pretty good.